All right, so this is Math 110 help here. And just go ahead and let me know if you have any questions. We'll stop, we'll rewind, we'll get going. This is one of the questions that was brought up, and this is a continuity one, so hopefully you guys can read that. So this would be some kind of piecewise function, I guess, right? So the f of x would be sort of defined by this looking function here, a rational function, on part of the domain, so that would be like wherever the x values are less than 2. We don't have to graph it, but if you wanted to think about this visually, here's 2, and looks like that the graph, however this looks, is going to exist over here, less than 2, right? And then this graph right here, if this was in blue, let's say, so this overall function is going to behave differently in this region, okay? So we won't have to graph them, but what we want to do is we want to find a value c, which is sort of an unknown piece of this second part that makes this continuous. So I don't know what this graph looks like just offhand, but let's say it looks like something like this or whatever, okay? Let's say it looks something like that. So what we want to do is we want to find out what this y value is that's going to be the value just at the boundary there, okay? So, and then we're going to use this value to let this part equal that, and then we'll solve for c. Because the blue part, you know, it can't start up here, it can't start down here, it has to start right here. So it has to have a y value at this 2 value. The y value has to be the same as what this function is coming towards. So I say coming towards because it looks like if you just go ahead and plug 2 into this first problem, we're going to get over 0 looks like here, right? 4 plus 2 minus 6, that's going to be something over 0. And so if you just plug in 2, there's going to be no value. It's going to be divided by 0, so that you can't do that. So what you're going to want to do is you're going to want to find, looks like the limit as x approaches 2 here for this rational function. Now, could you plug in a value like 1.9, 1.99, 1.999? Yeah, you could do that a few times if you want. And I'm assuming you don't have a graphing calculator for this question, like on a test, right? So you can't just graph it and then just see. So you could, you know, if push comes to shove and you freak out on the test and you're like, oh, I don't know what to do. Just, okay, as this comes up to 2, just find out what y value this is. So plug in 1.9, 1.99, 1.999 if you want in for x, and find out what the values are, and then you kind of have an idea of what that limit is, like what it's moving towards there, okay? But if you don't freak out, you might want to just do this. So we can't plug in x equals 2, so let's factor the top and the bottom. And this looks like it's going to be what? X minus 2 times x plus 1. And on the bottom, looks like x plus 3 times x minus 2. Okay. So factoring trinomials, we're good with that? Everything's okay there? All right. So if we do that, it looks like we can actually simplify this by dividing out the common factors. And then really, because this function is not defined at 2 anyways, we don't really care what kind of f of 2 is. For this one, because it's not really defined. So we are just looking for the limit. What y value does this graph approach as we get closer to 2? So this is really what we're trying to find anyways. So this is now limit as x approaches 2 of x plus 1 over x plus 3. And because now this 2 is not a problem to just plug in for x anymore, because it was a problem here, right? We couldn't do it because it's divided by 0. So it's not a problem. So then you just go ahead, and this is 2 plus 1 over 2 plus 3. And the reason why in all these limit questions that you can just plug this value of 2 in, because you want to think about this, as x gets infinitely close to 2, like as close as possible to 2, then this x is going to be as close as possible to 2 as well, and this one's going to be as close as possible to 2. So infinitely close to 2 is pretty much 2. So you just substitute. That's why we can do that. So this is going to be 3 over 5. That look good? So if it's 3 over 5, what that means is this y value is going to be 3/5. And I probably should take this graph away because I don't think this is what it's going to look like. But anyways, but this is now the value that is our target for this function over here. Okay, so I want to find out what the c value is to make this function equal 3 over 5. Because you see the blue function here? So it has to kind of be at 3/5. It has to be at 3/5 in order for this to be continuous, in order for it to continue on. You see that? So if the y value is 3/5, I'm now going to erase this part, and we will let this second part of the piecewise function equal 3/5. So we're going to go c over root 2x squared plus 2x equals 3/5. Or c equals, let's see, 3 root 2x squared plus 2x over 5. Now, the x part is going to be where x is 2, right? So now I can just replace x for 2 because all I need to find out is c now. So let's carry on with that. So it's 2 squared plus 2 times 2 all over 5. 3 root, what's that? 8 plus 4 is 12 over 5. Root 12 over, sorry, root 12 all over 5 looks like. That could be simplified. That's the value. I think that in, correct me if I'm wrong, but in your math, your calculus class at university here, how much do you have to simplify it? Is it okay to leave an answer like this, or do you have to have it in simplest terms, or just as okay? Okay, because this root 12 could be simplified, right, to was that 2 root 3 over 5? So this would be 6 root 3 over 5. So either one of those. Now, to double check my work, we should graph it maybe, and then just see kind of what this piecewise function looks like. Okay. Okay, so I've got this graphed on Desmos now, and we'll just go full screen here. So the red graph is the first function. So up to number 2 looks like this, coming up to there, and that's where it would stop in this piecewise function. And the blue graph, when we have our c value in it we calculated, would start at x equals 2, and look at that, it's at the same point. That's the intersection point. So it would be like this. So the graph would look like this. It would come up here like this. It would hit this value, and then it would kind of like curve down here like this on the blue part. It would be kind of a concave up sort of thing like that. Okay? And that's a good way to check to see if we've done this right. So here we go. It would look something like this, right? It would go like there, boom, and then it would kind of come down like that. That's what that would look like. Okay? Piecewise function? Good? Any questions? You good? Are you sure?
I'm good.
Because your dad's going to ask me if you're good or not, so I need you to be honest with me.
No, yeah.
Okay, I'm just kidding. I'm just kidding. Okay. All right,
The notation, when we do that, we do have to take it from the left and the right side, right? For this example, we do have to take the limit from the left for the first one and from the right.
Okay, good point. Good point. Yes, technically, because x is only defined for this left function on the left side, you're taking the limit as x approaches 2 from the left, correct? That's right. So if there was some kind of gap or jump in this function alone, then it might show up as does not exist or something like that. But if there is a limit, then it should be good. But yeah, technically you are thinking of it as a left-hand limit here, and then this one as a right-hand limit. But yeah. Okay, so let's take a look at the second one here. Is that my phone or is that yours? Oh, it's over there. Okay. All right. Josh. Okay. All right. Now this one says limit of x squared plus x minus 6 over the absolute value of x minus 1 as x approaches 1. So what is this limit? Okay. So what you could do here is you could split this up into two limits, like a left-hand and a right-hand limit. Usually with the absolute value, you can think of it that way. However, as x approaches 1 here, so if we just take a look at this function alone, that absolute value function is sort of like a, well, this would be the line x minus 1, so a slope of 1, and it would kind of pass through -1, right? That would be this line. Now the absolute value says that all this negative stuff has to flip over to positive. So that's what this graph alone would look like, which means, okay, the reason why I just show you that, which means that as x approaches 1 from either side, like here or here, then the value is going to be extremely close to 0, we know that, but it's always going to be positive. It's always going to be positive, okay? So as x approaches 1, this absolute value sign, you would only have to consider the fact that maybe it's negative on one side and maybe it's positive on another or something like that. You would only have to consider that if you knew that one side was negative, one was positive. So really you could actually just eliminate the absolute value signs because this is always going to be positive in here anyways. Okay? From either side, it should be, right? Because, again, because those absolute value signs, if x was approaching 1 from the left, so if it was like 0.9, then 0.9 minus 1 is negative inside, but then the absolute values make it positive, or drop that negative. If it was approaching 1 from the right side, then it would be 1.01, let's say, minus 1. That's a very small positive value. Absolute value signs kill it anyways, it just becomes positive, right? So this is always positive. So actually you can treat this just like there's no absolute value signs. Does that make sense? If that wasn't the case, then probably what you'd have to do if it was some other like, limit, blah, 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 and you had some like absolute value of some polynomial here, right? What you could do is take, especially if this x was approaching the value that, well, let me just say this. What you could do is turn it into two limits where on one side of where this thing flips is negative, and then also the limit, this is really messy, and then you could treat this as positive. You see? So you could kind of take two-sided limits there, if that makes sense. Yeah. So you kind of have to split that absolute value, because remember, absolute value signs, really, that value could be positive if x was a certain set of values, or this thing could be negative inside if x was another certain set of values. So you would, in math before calculus, you would say if it was absolute value of 2x, you would say for certain values of x, like less than 0, this would be negative 2x. And for values of x greater than 0, this would be positive 2x. Remember, that's the two options. So you could do that if you had absolute values, use those two options, find two separate limits. But for this one, I think this should be just the same. Now, I may be wrong, but this is what makes sense to me right now. So I think this is right. If it's not, we'll find out. But anyway, so if we plug x equals 1 in, we got a problem because we got 0 on the bottom, no good, right? You can't just say it doesn't exist, let's move on. Can't say that. You have to first of all figure out, can I factor this trinomial, and would there be a factor of x minus 1 up top that I could eliminate that would simplify or make this look differently? So this is x approaches 1, and I'm going to factor this top one into, let's see, x plus, is that plus 3? And then x minus 2 over x minus 1. Okay, so do we have any factors that can cancel out or divide out? No, we don't. We have x plus 3 on top, we have x minus 2 up top, x minus 1. So if we factor this correctly, which we did, there is no way to simplify this. So now you have to take a look and say, okay, so it looks like we've got a problem here because I can't get rid of this. I can't divide that out. So now what I would say is this. As x approaches 1, now just think about the values that are really close to 1. If this x value is going to be extremely close to 1, it's going to be pretty much like it's 1, right? So this is going to be pretty close to 1 plus 3 times really close to 1 minus 2. And down here, this is going to be really close to 1 minus 1. But it's going to be, remember that absolute value is there, so this is always going to be positive. Okay? But it's going to be a really small number. So you've got, and it might be easier to consider this original one before we factored, but 1 plus 1 minus 6 is negative 4, 2 minus 6. So this is going to be pretty close to negative 4 up top, and this is going to be positive, but pretty close to, it's going to be pretty close to 0, 0.00000, right? Something like that, right? As it gets closer to 1. So I would say this, and there is a more advanced way to figure this out, but you guys aren't supposed to know it yet, but I'll tell you. But your profs you'll be in trouble if you use it in Math 110. And it's called L'Hopital's rule. Yeah. If you took AP with me, you know about L'Hopital's rule. But my son got scolded because he was using L'Hopital's rule once. He's like, hey, are you cheating? Are you using Chug or something or whatever? Chug? What is that one? The site you're not supposed to go to? Chegg? The site you're not supposed to go to that get all the help online? Anyways, so he's like, no, I just took AP. I know. Okay, so he can't do that. So he can't use L'Hopital's rule. Do you know about that one? Okay, I'll tell you later. But it's a good way to check. But I would reason it through this way, saying this is going to be a negative value. This is going to be a positive, very small value. So this looks like it should go to negative infinity. Okay? Because you have a number divided by something that's super small, close to 0, which means it gets really big. Make sense? Yeah. Okay. So what we'll do is we'll graph this too, just to double check that. Okay, so we graphed it off screen there, and the graph kind of looks like this black graph, and certainly this graph does go to approaches negative infinity here at x equals 1. Okay? Now, L'Hopital's rule, at this point, they don't expect you to know this, but let me just show you this because it's so beautiful. If you want to find the limit for a rational function, so you have a function on top and a function on the bottom, what you can do is you simply you take the derivative of the top and the derivative of the bottom, and you actually just keep doing that until you can plug the value in and get a value. It's a little more complicated than that, but L'Hopital's rule says that this limit as x approaches 1 would be like f prime of 1 divided by g prime of 1, I think, if we can put it that way. So whatever that ratio is the limit. So that's the limit. So what's this derivative? That's 2x plus 1 over 1. So if I put 1 in there, what's that? 2 times 1 plus 1? Does that work? Doesn't work. 2x plus 1 over 1. That's 3. Did I write that down right? Oh, absolute value. Okay, so this actually isn't going to work because it's not an indeterminate form. So this one actually only works if you have, like when you plug this value in, if you get 0 over 0, or if you get infinity over infinity or something like that, right? Or 0 over infinity or something like that, then L'Hopital's rule will probably hold true. But like I say, if x squared minus 1, so something like this would work because if you just plug in 1, you get 0 over 0. So then you could just go ahead and take the derivative of the top divided by the derivative of the bottom with that in there, and then that you get your limit. So I should qualify that. It only works for indeterminate forms, 0 over 0, infinity over infinity. But you don't need to know that for 110. So yeah, shoot, I thought this was going to work. I thought it was going to work for this one, but it didn't. Okay. All right. When I look at this question here now, prove that sine squared x over 3 plus cos x is greater than 0. You're basically asked to show some way that this cannot be negative, right? That has to be positive. So the top one is pretty easy because so first of all, sine squared x, you know that actually is the same as sine x all squared, right? The squared in between the sine and the x part, that's just a way to drop any confusion between this and this, because that's totally different. Sine of x squared is totally different than sine of x all squared. So they put the 2 here. Okay, so if we have a squared, if it's squared, sine squared is always positive. Okay, so in your proof, you might just say something like sine squared x is always positive, and I don't know if they need more reason than just showing that, because it's a squared quantity. I don't know. You know what I mean? So squared quantity, try to write neater than me. Now, here's the other interesting thing. So what I would say to this is, why is this always positive as well? Because if this is always positive up top, this always has to be positive. It can't be negative, or else this isn't true. And what I would say to that is, the key is in the cos x here, which is also going to help us with the sandwich theorem, or also called the squeeze theorem, right? I actually looked at some of my old textbooks after you text me that thing, and on my old calculus textbooks, it was like sandwich theorem was like the big title of sandwich theorem. So it's like, it used to be called the sandwich theorem. But this is going to be important when we talk about that too. So what you have to realize is that the graph of cos looks like this, right? Periodic function. It has a maximum of what value? Remember? 1. And a minimum value of? -1. So if cos x never gets less than -1, then 3 plus cos x will always be positive, because the most negative that can be is -1. So I don't know how you want to write that, but since cos x is, and I would probably, let's write it like this, cos x is between -1 and 1, 3 plus,
no, I'm happy I did this one.
did you do this one right? Okay.
Yeah.
So, so then 3 plus, I don't know how you want to write this, a value no less than -1 is also always positive. And again, if there's a different way they want you to show that or write that, I don't know. But that's what. So does that make sense?
Yep.
Yeah. So these little tricky things, and with the squeeze theorem, we'll do some examples of this. We'll do some squeeze theorem stuff too. That's going to be really important. Like sine x is always between -1 and 1. Super important. Cos x between -1 and 1. That's the basis of most of your squeeze theorem questions probably that you'll get. Okay? We good on this?
Yeah.
Okay. All right. So for this one here, that's a pretty complicated function, right? And if you just plug 0 in, you got a bit of a problem where over here, right? So cos of 1 over 0, that's no good. Is 0 a problem in this part though? So sine of 0 is 1. 1 squared, it's okay. 3 plus cos, no, I'm sorry. Sine of 0 is 0. 0 squared is 0. But cos of 0 is 1. So 3 plus 1. So you've got 0 over 4 here. That's not a problem, but this is a problem. So you want to tackle this one by using the squeeze theorem. And how do you know? Because if you have a limit and you have cos, if you can build this function from the cos function, where you know what the limits are of the cos function, like the range, if you can get this whole function from a cos function or a sine function, then you can use squeeze theorem. So let me show you. So we know that cos of anything, let's say w, is always going to be between -1 and 1, right? And can we start there? Yeah, we can start there. It doesn't matter what w is. So w actually could be 1 over x. Does that make sense? So cos of 1 over x, doesn't matter what x is, it doesn't matter, as long as this is defined, the output values will have to range between -1 and 1, because there's no number in front. If I put a number in front, then this would go to 2 and this would go to 2, right? Okay, but they don't. So it's just a cos. Now, this right here, this function, I mean, we could piece this off, I guess, if you want, and we could say, you know what? If I multiplied sine squared x by cos, that would also affect this inequality. Wouldn't do too much. All you'd have to do is just multiply sine squared x over here and sine squared x over here. And then if you multiplied by 1 over 3 plus cos x, it would look like this. 3 plus cos x over 3 plus cos x. So really we take this whole thing and we kind of multiply it by the cos. Now what that changes inside here, obviously that now builds our exact function that we're concerned about. So just let me copy this down. Times cos of 1 over x. Now this is times -1 and just times +1. So in essence what we've done is changed this thing using the characteristics of cos into this function versus this function. And if we could find so this is x approaches 0. So if I knew or could find the limit as x approaches 0 of negative sine squared x over 3 plus cos x, and if I could also find the limit as x approaches 0 of positive sine squared x over 3 plus cos x, if I could do that, if I could find the limit, and if they were equal, then you've got squeeze theorem to help you. Squeeze theorem gives you the answer. So let's check these out. So can I just plug 0 in? And like I mentioned off the hop there, it actually is okay there, right? So this is negative 0 over 4. And this one is positive 0 over 4, which is still just 0, right? So this limit is 0, and this limit is 0 as well. So if the two boundaries, so what happens is those functions, they come, and as x approaches 0, their respective limits are both approaching 0 at that point. So if we know that this function has to have output values between this one and between this one over here, then at this point where the limits are the same, that means the middle one also has to have the same limit of 0. So let's take a look at this. Yeah, so cool. So cool. I looked at this today, I'm like, that is so cool. I am such a nerd, but that is so cool. So check it out. So here's our actual function, okay? Now if we just look at this graph, I know as x approaches 0, I can see what my limit is, it's 0. But let's say you didn't know that function because we don't know how to do this just algebraically, but if we could manipulate the cos function and I knew what this one was, check that one out, you see? It's coming up there as a limit of 0 at 0. And this one, this one too, check it out. So they're both coming to the same limit, and this settles right in between them. So it kind of like pops down and kind of almost looks like it touches there, and then pops back up and then down. It kind of just wiggles through there, and then it just gets squeezed totally inside there. So that's why the squeeze theorem works. So it doesn't work for everything, but especially if you have a cos there, limit with a cos, you're like, I can't plug things in, what do I do with the cos? Try squeeze. Or sine, try squeeze theorem. Now, I think there was another one that I just randomly tried. How did I do this? Oh, yeah. Yeah, I was just thinking about another function that we could use squeeze theorem for. So this one here, if you wanted to find the limit as x approaches 0 to something like this, actually, let me just see if I can copy that. I don't know if this will copy over into my notes, but I'm going to try. Yeah. Isn't that great? Okay. This is so great. All right, so let's do this way. Let me just take a snapshot here. Robert used to see me do this all the time, didn't you? Yeah. Okay.
I do it now myself.
You do it now yourself?
Yeah, on this.
Nice. Snip. Okay. So yeah, with this one, if we wanted to find the limit as x approaches 0 for this one, then we could use the squeeze theorem as well. So I would encourage you to write this down if you want to just kind of see how this works. This one's maybe a bit easier. Let's see, is it? Yeah, I think we want to do squeeze theorem on this one. Okay. So if we plug in x equals 0, we got a problem because we got 0 on the bottom there. You can't just divide. You can't take a common factor of x out here, right? You can't pull an x out from inside a trig function. That doesn't work. Can't do that. So what are we going to do? We could rewrite this as, like, this whole thing right here could be, don't write this down yet, but it could be x over x plus sine x over x. So we could split it up like that. Then I can see that this simplifies. That's really nice. And then, do you remember seeing this, the limit as x approaches 0 of sine x over x?
0.
Yeah, 0. So let's actually do this then. So the limit as x approaches 0, this thing can actually be split up into these things. And like I say, this is not really classic squeeze theorem, I guess, like the other one. But anyways, if you get a question like this, if you can simplify this, that's great. So this is actually limit as x approaches 0 of 1 plus the limit as x approaches 0 of sine x over x. And then this is not 0. This is 1. Okay. That's 1.
Oh.
Yeah, that's 1. I'm like,
oh yeah, the 1 minus
something didn't feel right. Yeah, because that graph is like something weird like this, and then it goes up to 1, right? Is something like that?
I confuse it with the cos one.
Yeah, the cos. Yeah.
1 minus cos x over x is 0.
Yeah, so this is actually 2. There we go. Because I think, yeah, that looks better. Because here's the graph. So there's, as x approaches 0, it does approach 2. So that's not necessarily squeeze theorem. I guess squeeze theorem more often comes when you have multiplied by cos or sine. Yeah. All right.
Back to the less important stuff.
Back to important stuff here now. Okay. So from the definition of a derivative, this is what we're doing, right? Using those formulas 1, 2, from the definition of a derivative, right?
Yeah, we're basically just using the second.
Using limits. Use the second formula.
Yeah, the h.
Okay, so you're using this one. Yeah, okay, so the limit as h approaches 0 of f of a plus h minus f of a over h. I like that one better than the other one. With this one, you have to expand, gather like terms, factor an h out.
Yeah.
With the other one, you got like a polynomial, you have to factor the polynomial. So instead of expanding and taking one h out, you got to factor a binomial out, which sometimes can be trickier. So I like this one better. All right, so f prime of 2, what we can do is say, okay, a is 2 then. Right, so we could just put 2 right in, and we're going to get our answer. If it was just f prime of x from the definition of the derivative, then what you'd have to do is you'd have to leave a in there, or I guess you could just put x. You could put x in this one. You can't put x in the other one, but you can put x in this one, and then just you end up with an expression. But for this, we're going to put a equals 2 here. So this is going to be limit as h approaches 0 of, where's my function? Oh, okay, right here. So I'm going to go 1 over, we're going to do 2 plus h plus 1. See that? Minus f of a, which is f of 2. So that's going to be 1 over 2 plus 1. All over h. Now let's just stop and check. Does that look good? I took the x here and I put in a plus h, which a is 2. So 2 plus h goes here. There it is right there. Good. I minus f of a. What is a? A is 2. So I just put 2 in for x there. Okay? Following me? So let's simplify. So I've got 1 over 3 plus h minus 1 over 3. All over h. Okay. What we're going to have to do is we're going to have to simplify the top, so we got to get a common denominator, right? And add, so let's combine that into 1, so we get to 1 kind of fraction there. So in order to get a common denominator, this one needs a 3 on the bottom, and this one needs a 3 plus h. So we just want to get a common denominator that way. So that's going to be 3 minus 3 plus h all over this 3 times 3 plus h. Kinda all over h. Kinda did a couple steps in a row there. Let me know if that bothers you. You can pause and explain. But here's the 3 that I got, and minus 3. Oh, wow, I just did a minus 3 plus h, I guess. We'll deal with that later. Now, when you have a rational, so here's one rational right here, and if like a fraction, if you divide by something else, it's the same as just writing, this times this in the denominator, right? Because it's like you're flipping and multiplying. So if you have h over 1 as what you're dividing all this by, you flip that, it's 1 over h, then h just becomes a factor in the denominator there. So if you have like 3 over 5 over 7, that's the same as 3 over 5 times 7, right? So if you divide, you just put them together as factors in the denominator. That's a little shortcut. So what is that? Okay, so I'm just gonna put h in here. So this is gonna be 3. I want to do 3h. I don't know. 3h. Okay. What disappeared? 3. That's minus.
Minus, yeah.
Okay. Okay. So yeah, nicely we have h approaches 0. So that's 3 minus h. 3 minus 3 minus h up top. And 3h times 3 plus h. Yeah? Okay, so that's just going to be negative h on... oh, where's my limit sign? Naughty. H approaches 0, right? You got to write that limit sign every time, right, Rob? That's what I taught you. So negative h all over 3h times 3 plus h. You could multiply that in, but wait, what? Don't have to. You can, don't have to. When you're trying to factor stuff, when you're trying to simplify, lots of times, multiply everything at the top, gather like terms, factor something out. But in the denominator, you can leave the factors alone. If it's don't multiply it in and get one big long string polynomial. Just leave the factors alone. Why? Because in all these cases, what we're trying to do is trying to get rid of an h on the bottom as a factor, see? So now those h's are gone, which is the problem, because if h was 0 before this elimination here, then we have 3 times 0 times 3, which we can have a 0 on the bottom. So now what we have is we just have negative 1 over 3 times 3 plus h. And if I just go ahead and say h is extremely close to 0, so I'm going to put a 0 in here, I don't have a problem. So that's 3 times 3 plus 0, or negative 1 over 9. And I believe that should be our answer. Let's go back to, this was where I got this from. So this is your 110 manual that's online. It's right here. Right, remember the U of R site here, 110 manual. And this was the question right there. So go to 45, look at that. Yeah, do we have negative? Yeah. Do we have negative? Okay. Yeah. Okay. Any questions about that or anything else you can think of?
Looks good to me.
All right. Okay.
Feeling a bit